Well, welcome back everyone so far. Looks like we've got an even split, two in class, two in Zoom. So we'll be all set in just about a minute. Well, we made it, folks. Looks like we can get started. So we're now in section 4.1. And just a word of wording about 4.1 is it starts out pretty intense, but the whole course isn't going to be the most abstract stuff, problem after problem, section after section. This is kind of the hump that we get over in linear algebra as a class. What makes this a pretty abstract section is we're talking about vector spaces as things beyond a list of vectors, or even beyond, say, arrays like in matrices. We're going to look into function operations, so we'll look into functional vector spaces. And it gets even more abstract. If you want to see a pretty exotic vector space, that's what this optional reading is all about, that signals are vectors. It's a pretty cool reading there. Other things we'll be doing today is taking a look into reviewing continuity to help us out with some of the vector spaces we're going to be working with. And before I forget, we're also going to start off by returning to that conjecture we were thinking about with the Cramer's rule in class last time. I don't have too many more announcements other than that, but any questions or comments to start us out, folks? Okay, well, let's jump in first by taking a look into Cramer's rule. The conjecture in class was a really good one. We saw something that was a pretty cool pattern where this matrix right here, if we were to take the determinant, we absolutely wanted to use properties of determinants because that just simplifies the process. We turned it into an upper triangular matrix really, really quick that way by using properties. And then the determinant just came out to 6 by multiplying the main diagonal, which is really nice. And then when we start to use Cramer's rule, I backtracked on some of the computations that we did in class because I was pretty worried about plugging 082 into, say, column 1 right here to get a result out. But when we checked it in class, it looks like we did it both ways. It came out of the same answer both times. It turns out that was a fluke, though. Think about the row operations we did on this one. The row operations we took was we took 2 times row 1, added it to row 2 to eliminate that entry. If you do that here, no change because of that 0. That vector was lucky in a way. The next row operation we took to get to upper triangular here with properties of determinants was we added row 1 to row 3. Again, no change on the vector b. So it's as if we did the row operations on that same vector b because it's no change every time. That's why we got the results both times. But if you change that vector b just a little bit, place a 1 right there, we get a pretty fast counterexample. So that's what I did over here to kind of reason through what's going on with this. I plugged in a 1. It took me a while to notice the row operations didn't affect the b, and that was the main crux of it. When I plugged in a 1 and used the original matrix, 1, 5, negative 1, copied down, column 3, negative 3, 1, 4, working out this determinant, I got a 45. And I used properties of determinants again on this one. But if you use the reduced matrix, sorry, let me scroll this a little bit better. If we use the reduced matrix, there we go. This one right here, copy in 130 into this location, negative 371 into this location, drop in 182, it does come out as different on that one. Again, it's all because of the 1 right here affecting that row operation. So in general, the idea does work. You can use row operations on this determinant and reuse this again, but if you did that, you have to maintain the same row operations on this vector here and then reuse the resulting vector. In fact, it just feels like you're going to an augmented matrix doing row reduction till you get upper triangular or something, and then running it through Cramer's rule with a more convenient system. So it's like you're doing kind of two things at once. And if you did take advantage of those ideas, I would say no harm done, even in an exam setting. If you're using other tricks to get through the problem. But that's the counterexample of what went wrong, what went right in class, or versus this new vector b. Does that make sense with the questions we were thinking about last time? Okay, those are always pretty fun, cool conjectures to think about. So thanks for asking about that and posing that. I'd like to try to solve them live, but sometimes with some of these things, it's one of those things where you have to do some homework, come back to it, and see just what really is going on in the background. So pretty much that's Cramer's rule in a nutshell. If you do decide to use properties of determinants, you can row reduce the original 3x3 matrix A, or even a 2x2, do the same row reduction on the right-hand side, and you can take advantage of some pretty fast determinants getting through Cramer's rule. Next thing we took a look into was vector spaces, section 4.1. But really, we just kind of stared at this. We related to this to Euclid's axioms to kind of remind us that we're not doing anything too different. The revision you see here is mostly spelling and a couple of grammar spots I had to fix up. We'll see along the way, nothing too major. So the vector space, the first thing we have to say about it is it's a set. You cannot start with the empty set. So that's one, I mean, that's a good idea, right? If we have a theory that involves a set with nothing in it, an empty set, then we're coming up with a whole bunch of facts about nothing. So that's a good idea. We insist that you actually have a set containing at least something inside there. Even if it's just the zero vector, that would qualify. So we have a set of objects, we're going to call them vectors. And vectors can be pretty interesting things. Let's pause right here because we've already seen some great examples of vector spaces. So while we're thinking about that, we've pointed to these notes a couple times. One good set of vector spaces is Rn. This looks like an example in R3 because there's 3 entries. And the algebraic properties of vectors, a lot of this stuff is just the axioms of a vector space. The major thing about the vector space is having a notion of vector addition. So just add vectors by adding their entries component-wise, and scalar multiplications, just scaling each component. So chapter 1 was just one big example about vector spaces and transformations between vector spaces. Then section 2.1, same idea. We have arrays now. A is an entire m by n matrix, so m rows and columns. Same with B. Vector addition, that really sounded weird back in the day when we called these vector additions, but it truly was because we now have Rm by n of vector space through the similar operation of vector addition and scalar multiplication. Really doesn't feel like we did anything too different, except we might have just took a really long vector and split it into several columns and did the same kind of additions, same kind of scalar multiplications. The zero vector looked like these kinds of things. It seems weird to call it a zero vector, but these two properties satisfy every single property 1 through 10. So it's right to call matrices vectors if you're viewing the set, the collection of m by n matrices, as one entire vector space. It just seems like an unfortunate uses of language, but it would be correct. So properties 1 through 10 follow for matrices as an example as well. And part of the goal of these notes is just to extend these examples to other things a bit more interesting. So we have 2 major properties, also just restated down here to make them feel more important. Closure of vector addition says if you have a true vector space, anytime you go to use the operation of vector addition, you can't leave that space. U plus v is always inside the vector space v. And same, when you scale a vector v, it's impossible to leave the space. C times u is always in the vector space v as well. So these are the 2 major things that we're going to check as homework problems, potential exam problems, to determine if something might or might not be a vector space. The whole set of axioms is a lot, so I'm not going to ask you to prove, say, 1 through 10 on any example. That'd be a lot of work. A lot of these things we kind of take for granted as properties. Vector spaces have a commutativity property. U plus v is the same as v plus u. Likewise, there's associativity. There's an additive identity. There has to be a zero vector so that when you add to that vector u, For any vector u whatsoever, you get vector u back. There's an additive inverse. And again, so far, this is just looking in those same properties back in 1.6, or excuse me, 1.3 and 2.1 all over again. These are distributive properties. These are kind of associative properties with scalars and a vector u. And this is a multiplicative identity type of property for a scalar, the scalar 1. So these are all the great algebraic properties we would like to have. Down below is even more properties, but these aren't axioms any longer. Every one of these properties, 1 through 5, can be proven directly through axioms 1 through 10. So every one of these axioms is critical. If I try to derive, say, axiom 7 from the others, we might have kind of a hard time doing that. Let me take a look here. Yeah, it looks like trying to derive, say, 7 from anything else we see on the list might just be impossible. So every one of these statements is critical and important in some way. But these ones, we could prove these directly from the axioms right above. And these are just additional properties. The zero vector turns out to be unique. The additive inverse is unique. Taking 0 times a vector as a scalar multiplication gives us the zero vector back. A scalar times a zero vector will always give you the zero vector. And if you take negative u, that can just be reviewed, this negative right here, as just a scalar multiplication. So these are additional facts that can be derived from the axioms above. And, well, they're just more algebraic properties that we tend to take for granted when we're thinking about a vector space. So it's a lot of stuff that goes into this. 10 axioms is quite a lot, but there's just algebraic properties that we've been taking for granted all along in chapter 1, chapter 2 as well. Any questions about the axioms or the theorems below? Okay, well, let's start to delve into this kind of stuff bit by bit. First example 1 right here is really just kind of a warm-up example. It's just a reminder that we've seen vector spaces before. If n is greater than or equal to 2, Rn is a vector space. We just take the same vector addition, scalar multiplication as we've seen in chapter 1. And one thing that's going to be critical as we go through the notes is writing down the zero vector. Sometimes it's vague what that even is, depending on the space we're working in. So as a warm-up problem, the zero vector for R5 would look like this. We write out like that. If we know what contents we're working in, we want to be really descriptive, we would write it this way. So that is the zero vector in R5. So nothing new from section 1.3. But one thing that gets a little bit tricky in these notes is when we think about vector spaces, the very first thing that it's telling us in the definition is it is a non-empty set. So really by its nature, a vector space is a set, and you have to study set theory to some degree to get a really good intuition on how to work with these things, especially when we go into subspaces, which are just subsets. So if we were to write, say, R5 as a set, here's what it would look like. The vector space R5 is defined to be this. One big set, so we indicate a set by the curly braces here, much like the set H down below. We write down the typical object in set builder notation. The typical object will have 5 entries if we're in R5, so x1, x2, x3, x4, x5. The little colon here, sometimes it's a vertical bar. It's just a way to say verbally, such that some condition has to hold. So the condition that has to hold to have a bona fide element in R5 is just that x1, x2, x3, x4, x5 are all real numbers. So that's R5 written out as a set. Nothing too spectacular, but you can imagine with set builder notation, this kind of stuff could get pretty convoluted pretty quickly. And here's an interesting set, just like before. It looks like it's a subset of R2 because there's two entries here written as a column vector. A, B are in R. That's not too different than saying X1, X2 are in R. But now we have an additional relationship, A less than B. And we'll have other interesting relationships inside that set. So this is the condition that must be checked for set membership. The colon here is just read as a such that. And the thing that comes first is just the typical element. You could say typical vector, but it's not guaranteed that H is a vector space. So we often call just an object inside a set an element. So R5 is the set of all elements such that there's 5 rows. Every one of the values are real numbers. And H is a different kind of set. It's the set of AB such that AB are also real numbers with a strict condition, A must be less than B. We'll show that H is not a vector space. I mean, there's a lot of similarity, but this condition turns out to be restrictive. We'll show it's not a vector space by showing closure fails for one of the properties. Really, it's just a venture looking into set theory and looking into closure properties again. So let's copy these down just for easy reference. And it might feel like the work we're about to do is similar to when we were looking into linear transformations or just transformations in general. And the instructions might have said, show the transformation T is not linear. We were looking for a counterexample, and same idea here. If we're trying to show the set H is not a vector space, we need a counterexample to one of the two closure properties here or here, either the vector addition property or the scalar multiplication property. C times U is in V. For all scalars C, all vectors U. I'll go for this property since usually this one's a little bit faster to work through sometimes. But if you get into tuition doing these in the homework for the addition property, that might be the one you need to check. First thing I would do is just try to visualize this space. This is an AEB plane you could write out, or XY plane, or X1, X2 plane. I'll write it as an AB plane to match up the notation in that set. So there's the A axis, there's the B axis. This 45-degree line coming through like this is the line for A equals B. Now we're either on this end or this end. And a quick way to tell is just to throw down a couple vectors. So if we put a vector, say, here, this would be the vector 1, 0. Vector here, kind of the call outs to prior work we've done. This is just the standard ordered basis vectors we're working with. This is the vector 0, 1 over here. If I can determine which vector is inside the set, this is the line that cuts them off. We'll know which side is in the set, which side isn't. So what we look into is the set membership condition. We're only picking real numbers, so this part is definitely something we don't have to check as carefully. I'm not going to put in a complex number here and try to plot it in the plane. But the thing we do have to check is this part, A less than B. So let's look into, say, that vector, 1, 0. A is playing the role of the first entry, B is playing the role of the second entry. We have here 1 greater than 0. Well, that means it doesn't satisfy this. Therefore, 1 less than B is not satisfied, and 1, 0 is not in H. So really, lots going on here. Think of the first entry as A, second entry as B. We had 1 greater than 0, so A is greater than B. That's a negation of this statement. Well, the negation, full-on negation would be A greater than or equal to B. We just wrote strictly 1 is greater than 0. But we needed the property, I wrote that weird, 1 less than 0. I must have been thinking of B when I wrote it at 0. we need the property 1 less than 0 to come from here for set membership. So 1, 0 is not an H. Let's check out 0, 1. For 0, 1, we have first entry playing the role as A is 0. It's less than the second entry playing the role of B as 1. That means the set membership condition is satisfied. Vector 0, 1 is an H. So this is in H. Anything on this line is not in H because this is not A less than or equals to B. So we throw out all these values here. And now every single vector in this side is inside H. So if we were to shade, here's what it would look like. And just to emphasize, here is the set H. Out on this side is H complement, but you don't have to write in any special symbols for that. So now we know what the set H looks like geometrically. We've found a vector that's actually inside H, 0, 1. We can give it a name if we like. Let's call this U. U equals 0, 1. We show directly through this property, A less than B. It's in H. So this is the property we had to check. And now to show this is not a vector space, we can find another vector U. It has to be inside the set H somewhere, add them together, and show we leave the set H. Or maybe simpler, find a scalar, find a way to rescale 0, 1 so that you just leave the set H altogether. So let's think about that. Let C be equal to something. So the idea here is if the closure holds, then CU is going to be inside the vector space V, playing the role of H on the problem here. We already have the vector U in H. H is playing the role of V. We just need a scalar so that we actually leave the set H altogether. Anyone see a scalar that might work out? Absolutely. -1 would do the job for us. Let's C equal -1. Let me take off the marks here so we can see this again. So we've got a vector U in H. I'll just write H over in place of V. We've got a scalar C in R. We picked -1. And we want to show this fails. Show this fails. That means closure would have failed, and that would mean H is not a vector space whatsoever. It's an interesting space. It's a half plane organized by the 45-degree line, but definitely not a vector space. So to check this out, we just go right here, do the scalar multiplication C times U. Then C times U is going to be equal to -1 rescaling 0, 1. This comes out as 0, -1. We do another check. We're always going back to this, A less than B. We can say here, entry 0 is strictly greater than, that's the A part, entry -1, that's the B part. That means membership condition has failed. We don't have the first entry less than the second entry, or we could visualize it as multiplies by -1, and we ended up down here. So over here, this is CU, if this is the vector U. We've clearly seen visually we've left the set, but checking with the set is a good idea since it's not always easy to actually graph what your vector space looks like. But 0 greater than -1 tells us CU is not in H. Our work is done at that point. We showed a closure property fails, so we can say, therefore, H is not a vector space. So that's checking out closure properties. If it really was a vector space, no matter what scalar you would have picked, you would have always ended up in that same space there. Well, any last questions, folks, on getting through this one? Okay, there's a couple problems just like this in the homework. Really all we're looking for is a counterexample. This was our counterexample, a specific scalar C, a specific vector U, showing one of the properties fails. Well, other things we can take a look into is the more exotic vector spaces that we've been teasing pretty much the whole semester. These are the same kind of things that we've been looking into in sections 1.3 when we define vectors. It was just a restrictive condition here that forced it to be a non-vector space. Other more interesting vector spaces that come up a lot, here's the misspelling that I fixed, is the set CAB. This comes up in calculus settings, differential equation settings, and lots more the more and more math you take, elementary analysis, and so on. CAB, C here stands for continuity. AB is just a closed set of real numbers from A to B. So if this was, say, C01, we're talking about the classification of all continuous functions having domain the closed set between 0 and 1. So written out as a set, it's the set of all functions such that the set membership condition is your function is required to be continuous, and it's continuous on a closed set. And that's a really important classifications of functions, because if you think about integration, every function inside this set is automatically integrable. It has an absolute maximum, it has an absolute minimum. It's a really nice set of functions. Functions are pretty bizarre things, but CAB, this is an orderly set. It has a lot of structure, however. It's surprising, but CAB is also a vector space. And this is where linear algebra just pretty much has its hands all over the place. We've already seen it intersecting with algebra, trigonometry. It's all over the place in calculus, differential equations, and so on. In differential equations, when you go to solve a differential equation, you're looking for a set of solutions such that the span of those solutions describes the total solution set. So we even use the linear algebra kind of terminology in differential equations as well. But there's lots of going on when you're describing CAB as a vector space. We now have to redefine, what do we mean by vector addition? What do we mean by scalar multiplication? And that's part of the notes that we are looking into over here on the function operations. So let's take kind of a breather on this. The main takeaway is this is what CAB looks like written out as a set, all continuous functions on the closed domain from A to B. But for the actual operations that we take, it's kind of fun in a way because we're going all the way back to this class. This is college algebra material. It was renamed recently to Pre-Calculus 1. And in college algebra, you define a whole bunch of new functions based on old functions. If f and g are two ordinary functions and c is an ordinary real number, we would have said scalar if we were thinking in linear algebra terms. You can define a whole slew of functions. Here's a whole set defined through here. Composition of functions is also important. But if you're only thinking in terms of linear algebra, these are the two that we're most interested in. Scalar multiplication is this, CF. If you want to define CF, it looks like this. CF at an input x, we're now using function notation, is defined to be C times the old function f at x. That's confusing in a way because when you look into these functions, that's just the name of the function. If you want to define it, you write out things like f of x equals, maybe it was x squared plus 3, for example. But f and g, that's just a name altogether. Likewise, CF is just the name of a whole new function. That's considered to be just one symbol, not two things whatsoever. It becomes two things algebraically when you apply the definition, the actual scalar c times the y output, f of x. At the same time, f plus g looks like we're dealing with two things and a symbol in the middle, but really that's just one whole symbol. The plus in the middle doesn't have any meaning. That's just the name of the brand new function. Over here, plus does have a meaning. That's ordinary addition of real numbers. And these are the two actual functions outputs, the y values for f of x and g of x. So the thing to get used to on these notes, the reading is kind of strange in a way. We have to train our mind to see this as just a new vector because f and g are coming out of a vector space, they're vectors as well. CF is just the name of one brand new vector, and F plus G is the name of some other vector at the same time. So that's kind of what college algebra or pre-calculus was going on about when they defined these kinds of things. And the ones down below, it was defined in kind of a finicky way. You might have wondered, why are we being so particular about putting this in? Well, that's just because F plus G is one symbol of a function, and that's just how it happens to be computed. So bringing this all back, other things we have to think about is properties of continuity. And this is just kind of a rehash of properties of continuity already back in Calculus 1. All we really need is the fact that if f and g are two continuous functions, whether you add them or subtract them, those are continuous functions. And if you scalar multiply them, we may not have said that in Calculus 1, but we sure meant it. C times f is one function as well. CF is also continuous as a function. Even in Calculus 1, this was written in kind of the linear algebra sense when they wrote CF and f plus g without the input x plugged in. They didn't say f of x plus g of x is continuous. They were precise when they said f plus g or f minus g is continuous. They were thinking about those ideas of the vector space, really. That's kind of a long discussion, but we're doing something totally different, so it's good to take our time to think about these new objects. Any questions at the moment with the function operations or about continuity? Okay, well, here's our brand new operations. Vector addition means you grab two functions, f plus g. The addition of them is this function, just a brand new name, the result of f plus g. The way it's defined is this way. Our book likes to use an input t, since x sometimes has a separate meaning, thinking of variables x1 through xn. F plus g at t is defined as f of t plus g of t. And to know that this is a real vector space, the two main things we'll check is the closure properties. To verify closure of vector addition, we have to explain why f plus g is inside the set CAB, which is a true vector space. But we just really look into this part. This is the set membership condition. We just need to know these new functions, f plus g, are continuous. That's the Calculus 1 tie-in. We can say, since f, g are continuous, how do we know they're continuous? We said they're in CAB. That automatically tells you those are continuous functions on the closed set from A to B. So that tells you they're continuous, but now we can just cite Calculus 1. By Calculus 1, we know f plus g must be continuous. The moment we say that f plus g is continuous, that's the set membership condition, we can immediately say, therefore, f plus g is in CAB. F plus g is in CAB. This new function is just one function. That's the whole symbol for it. It's kind of clunky. It's defined in this way, but it's a member of CAB. And that's what vector addition will look like for the space of continuous functions. So again, it's not anything too different. The thing that's different is every element of this set can be now thought of as a vector. Not like a point in the R2 plane. This is something more abstract, something we could never really plot. Even though this is a well-behaved, well-defined set, this is a pretty vast vector space. If you try to put a dimension to this, you will fail. R5 has dimension 5, but this one is infinitely dimensional, which means a lot of weird things happens inside of this vector space. Well, next one is scalar multiplication. Really kind of the same idea. We cite Calculus 1 material. If f is a function of CAB, it tells us f is continuous. So if we follow that same process, we'll say, since f is continuous, by Calculus 1 material, once again, we know CF must also be continuous. It's continuous on the same closed set from A to B. And that tells us automatically, therefore, CF, that's just the symbol for one additional new function, is in CAB. All the other axioms of the vector space properties hold for this new vector space. The ones we're looking to particular are these two closure properties. And another thing that's really important is, what is the zero vector? That's going to be our next part. But any questions so far looking into these ideas? Okay, next concept is, if it's a true vector space, and it is, we have to be able to somehow, some way, write down the zero vector. So write down the zero vector of CAB, sketch its graph just so we can get some intuition at what we're even looking at. And let me hide that down below. Well, first, these things are functions, so I wouldn't write down this any longer. This is more appropriate if you're thinking, say, section 1.3, vectors in Rn, or maybe even matrices, vectors in Rm by n. But if you're dealing in a function space, whether it's continuous functions or specifically polynomials, probably a better way to write a zero vector is something like this. F, G, and H could work, but I think Z is a logical choice, a lowercase z to stand for zero vector. So let's say let Z denote the zero vector. We wrote it down, we said Z is a zero vector, but what we should really do is also define it. This means then Z at an input T equals 0. We should be really specific about that. We can have 1, 0, but for this to be a true zero vector, this isn't good enough. It has to be 0 at every single input in A to B, so we should say for all T in bracket AB. So that's what defines a zero vector. This part right here is critical. The fact that it's not 0 just for one value. I mean, cosine goes to 0 at pi over 2. It's not the zero vector in CAB whatsoever, though. This one is. So don't forget this part right here. So this part is required to define the zero vector. Then if we were to sketch its graph, it's a pretty fast one, but visualization is pretty helpful for anything abstract. So when we can, we should. AB can be any real number with the assumption that A is strictly less than B, that this is an actual interval, not just a point. And we can't change the order here and make, say, A 30 and B 2. That would be an incorrect way to define closed interval notation. But I'll just put A generically here, B generically here. Looks like this is in the right positive end of the x-axis. They could be anywhere on the x-axis. The zero vector z of t then looks like this. Just thinking of a new color to write this in. Goes from here to here. All outputs go to 0. So that's z of t as a graph. So it's a strange new land. We'll be looking into the vector space CAB quite a bit in the upcoming notes. In particular, the chapter 4 is going to culminate in finally defining a basis and then the dimension of a vector space. And we'll look into justifying what we said earlier, that this is an infinite dimensional vector space. It's a pretty weird one. But any questions so far, just looking into this initial example? Okay, this is going to be the weird one for this class. It's so weird that there's a whole other mathematics class you can take that studies these kinds of things. So if you're curious about when you might see this again, the other class is functional analysis. studies vector spaces like these. A pretty crazy topic, really. It's kind of like linear algebra, but with things that are of infinite dimensional. Now, I said here, take a look at this section 1.3 before looking to this example, but we kind of already peeked at that. That was the vectors in Rn. Here's another interesting vector space. But what's kind of weird about this one is it's a set of all polynomials, yet polynomials are pretty nice functions. We know that they're continuous on the entire real number line, that they're differentiable infinitely many times. You still get a continuous result every time you differentiate them. They're wonderful functions. And the polynomials we're going to define have a domain that's all real numbers, but you could restrict the domain to a closed set AB, and the polynomials are just a subset of CAB, the space of all continuous functions. There's polynomials inside here, they just have a limited domain. So this has an infinite dimension, but the polynomial space Pn does not. This one is a pretty interesting vector space that might make you feel like deja vu when we look into it very, very closely. First, notice that subscript n down there. That's the critical thing that makes this not as abstract as it could be. Pn with a lowercase n, some books make it that a superscript. That's kind of strange. Our book went for a lower value here, subscript. It's going to be the set of all polynomials of degree at most n. So if this was P2, these would be a set that contains all quadratic polynomials, all linear polynomials, and all of the constant polynomials. When it says at most n, it includes everything below n, all the way down to degree 0. So that's why it has a term that goes t power of n, an minus 1, all the way down through a1, a naught, has just one condition. They're real coefficients. They're all inside the space R. So the set Pn, the space of polynomials of degree at most n, is a set of all polynomial functions P, such that you define P at T in this way, with the restriction that these coefficients are all real numbers. So Pn turns out to be a vector space, and the operations of vector addition, scalar multiplication are pretty quick to show. It's good to see it at least once, so let's write these out. Any questions first about the vector space itself? This turns out to be a vector space that we'll look into quite a lot. In a lot of interesting numerical analysis results, there's things called Laguerre polynomials, Legendre polynomials. A lot of French mathematicians put their name on it and they say polynomials, and it's used in all sorts of things in computer science. So we'll look into some really interesting examples with this polynomial space. But if we're just defining it as a vector space, we have to know what is vector addition. Key thing is these are still functions. So it's like CAB, the space of continuous functions. You take two functions, define P this way, coefficients run an through a naught, define Q this way, bn through b naught. This is not saying P is degree n. It could be degree 1 or it could be degree 0 because an could be 0 or non-zero. These can be any real numbers whatsoever. So for some scalars, which are now coefficients, we can say vector addition looks like this. P plus T, that's our brand new, or excuse me, not T, P plus Q. That's the brand new vector defined by these two vectors, P and Q, and Pn is defined by, takes a moment to write out, but P plus Q at T is just defined by adding up all the coefficients. Just like the functional space, it's P of T plus Q of T. And now it's just a matter of combining your like terms from back up here. That means it's an plus bn times t to the power of n plus an minus 1 plus bn minus 1 times t to the power of n, but we'll go through the dot, 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 skip down to a1 plus b1 times t power 1, so just t, plus, hang on, before I do that, That's supposed to be eraser. This flows a little bit better if you maintain the dot, dot, dot right here. So let me go dot, 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 because I'm skipping a bunch of terms. N could be a very large value. Then it's A1 plus B1 times T. Then combine the constant terms A naught plus B naught. Parentheses here aren't needed, but just as a way to visually group them, I included them even on the last term. So that's what vector addition looks like for this. It's not too different from CAB, but this time we just have an opportunity to combine like terms because we're just dealing with ordinary polynomials. Scalar multiplication is the same kind of deal. For scalar multiplication, we would say CF is defined by, we should be specific because I don't think we have defined C anywhere. So just to make sure we know what it is, let's just make a mention. C is in R. So now we know it's a scalar. Then CF has meaning. It's a new vector in the space Pn. And if we have to say what it is, CF at T is defined to be C times F of T. Again, it's just reiterating the same definitions from CAB, the functional properties. We take the scalar C, distribute it through this entire group, and we get CAN times T power of n plus, all the way down the line, C times A1 times T plus C times A naught. That's the scalar multiplication. And next is just saying what the zero vector is. So feels like deja vu again. Feels like we've done exactly the same stuff as we've done for CAB. But I assure you, this vector space is weird in how simplified it really is. CAB is the monstrously complicated one, but PN, it probably feels like something you've done before because you really have done it before. This is chapter 1 material. It just might not look like it because the notation feels so different. Let's write down the zero vector while we think about that concept. That this is really chapter 1. This is really section 1.3. Let's write down the zero vector Pn. Let Z be the zero vector of Pn. It's the same function that we define in CAB. It just has a domain that's all real numbers because we're not constrained to a closed set any longer. But if we really want to write it down as a function that fits inside here, you can. Nothing's going to stop you. Z of t equals 0 times t power of n plus 0 times t power n minus 1. I'm just choosing my scalars, my coefficients to be 0, plus all the way down the line, 0 times t squared. That's a t plus 0 times t plus 0. And sure, that simplifies to 0 altogether. But this is what z of t is for all t in R. Short version is just that z of t is 0. That would have been fine to say as well. But I just want to show how it fits into the space by choosing the values. Because once again, if you're thinking about this being really just a chapter 1 concept, this is the relationship or the hook to show that. Well, the example 4 is done. This is what that polynomial space Pn looks like. Any questions or comments at the moment? Okay, lots of things happened in chapter 1. What it culminated in is one of the major ideas in linear algebra. Linear algebra is all about vector spaces and the linear transformations between the two. And one critical class of linear transformations, the screen went out for a second there. One critical class of linear transformations is the isomorphisms. We'll actually be studying a particular kind of isomorphism in section 4.5. But let's talk about an isomorphism right now, just to relate what we're looking into. So that's what the blurb is down on below. The operations in Pn feel familiar to you as operations in Rn plus 1, then you're right. This is the same stuff. We're going to later on say that this is an n+1 dimensional vector space, just like Rn+1 is also n+1 dimensional. We'll say Pn is isomorphic to Rn+1. And looking into that word once more, isomorphic, iso just means same, morphic means form. What we're saying is Pn has the same actual algebraic structure as Rn+1. The only difference whatsoever is just the notation that you use to write down a typical vector in Pn versus Rn+1. If we did a transformation that looked like this, T goes from Pn, oh, that's a subscript. T goes from Pn to Rn+1 is defined by T takes a function P and outputs An. That's the coefficients that we defined up here. Next entry is An-1, all the way down to A2, A1, A0. So An-1, A1, A0. Then that's our isomorphism. All this is saying to do is go to your polynomial, peel off the coefficients, An, A1, A0, all the way down there. There's n+1 coefficients altogether, and you get a vector in Rn+1. This linear transformation, well, I already said part of it. This transformation is linear. It does not have a standard matrix, however. That's one thing that's weird about it. And it's because we're not going from Rn into Rm. This is a different kind of vector space. There's no longer a standard matrix to help us out with this one. You can still show it's linear. It's linear, and it's also 1 to 1. Because there's really exactly one way to define a polynomial. You just say what the coefficients are. And we said it right here. This is a 1-to-1 correspondence between polynomial, pull off the coefficients, big punchline in linear algebra. We do that everywhere. And these correspond into a 1-to-1 way. And it's also on 2. For every single n+1 array of values, you can just come up with a polynomial that has those same exact values and map onto it. So for example, if you have t of, maybe it's 3t squared plus 4t minus 1, this would be just a 3, 4 minus 1, and this would be for a transformation t, p2 into R3 for just a particular example down below. So this tells us the vector space Pn is not as abstract as we thought it would be. It's n+1 dimensional. It's a subspace of the scary one. CAB is where a lot of crazy things happen. If you're talking something beyond polynomials, the space of any continuous function whatsoever, that's where a lot of weird stuff starts to happen in linear algebra. But because the space Pn is so important, we'll study these kind of isomorphisms and use them for our benefit later on in chapter 5. Well, any questions at all, folks, with the polynomial spaces at the moment? Okay. Next, and pretty much the last concept on these notes, is the notion of a subspace. And this is going to be kind of the meat of this section. A lot of what we've been doing is just familiarizing ourselves with the new landscape, the 10 axioms, closure properties, and the new vector spaces that we're going to be running into in chapter 4. But these are kind of the major things we're going to be doing as the more routine kind of homework problems and the things that carry over quite a lot as well. So a subspace is a non-empty subset H of an already established vector space V. So the fact that it's not empty is important, but this word causes some trouble in this class. It's also a subset. And depending on your background, you may or you may not have done very much set theory, or maybe you're kind of rusty on set theory. That makes a subspace kind of a foggy, hard to work with concept. We need to know exactly what we mean when we say subset, because that's the first critical part of the definition. You have a non-empty subset. So maybe even before taking on this definition, let's just do a really fast subset kind of problem, just to kind of brush off the dust and get everyone on the same page on what we mean by that word right here. Let's just define some simple sets. Let's let X be, say, 0, 1, 2, 3, 4, 5, and 6. I'll let a new set Y be the set. Let's go maybe 1, 3, 5. And let me fix this formatting here. New set. Let's not use Z because that might feel like a zero vector. Let's call this one W. Let's let this one be 2, 4, 6, and 8. So to track this new definition, this is the new word that we're trying to work through. We can say first, let's relate Y to X. Y contains elements 1, 3, 5. So does X. 1, 3, 5 is inside here. So in a certain sense, Y is contained inside the set X itself. 1, 3, 5 is all here. So we would say Y is a subset of X. If you like symbols, it would be written down this way. There's a couple varieties for subset relations. But it would look about like this for one way to write down subset. It's like a sideways U. You're saying Y is included in the set X because all elements in Y are also in X. So that's the one that works out. That one's a subset. Almost works out for the set W. We have 2, 4, 6, but 8. 8 is not in the set X whatsoever. So we would say W is not a subset of X. In symbols, you might write it this way, W subset X, and then just put like an angry slash through it. Now you're saying it's not a subset of X because the element eight in W is not in X. There's lots of weird things you can discuss when it comes to subsets, but this is the main meat of it. To have a true subset, every single element in H is also in the vector space V itself. It's not the entire vector space necessarily, but it's just a smaller version. Well, any questions at all, folks, with just the idea of subset? Okay, well, beyond that part of the definition, we're saying H is going to be a subspace of a vector space V. If at first it's a subset, there has to be something in it, so it can't be empty. There's really some object inside that set H. And the other three conditions have to hold. It's got to contain the zero vector. And when you look in part A, that actually resolves the non-empty part. If it has the zero vector, it's automatically a non-empty set. There's something in it. But this is an important requirement as well. The zero vector of the larger space V has to be inside that set H as well. Now let me retune the color coding since the larger space V is a big part of this. So the zero vector of V is also in the smaller set that we want it to be a subspace. So this is one way to think about it. It contains the original zero vector. And the next part are just closure properties. We're closed under vector addition. If we take any two vectors in H, then the new vector, when we take their vector addition, it's also in H. So we're closed in H in that kind of way. Likewise, if U is a vector inside H, C is any scalar, then the scalar multiplication results in a new vector still in H. We cannot leave that space H in any way. So if it contains the zero vector, if it's actually a subset and you have two closure properties, that tells you H is a vector space in its own right, using the same operations of vector addition, scalar multiplication. So this is another way to just construct more and more examples of vector spaces. Subspace just means it's a new vector space contained in the larger vector space V that we're thinking of. Well, there's going to be lots of interesting vector spaces we're going to look into. The very next section, 4.2, is going to be one of the big ones. We'll call it a null space. Well, it's a big definition because it has three parts. The way to think about this one is, it might not feel too different if you relate it back to something we did all the way back in chapter 1, when we're looking into linear transformations. Let's open that up just to get a visual on it. When it came to defining a linear transformation, we had two major properties. Let me look for a definition that doesn't look too marred. That'll do the job. We had the property that if we looked into the vector addition u plus v, we can separate the transformation and do the vector addition in the codomain space or in the domain space. In a certain way, it's kind of like the part B right here. We're looking into properties related to vector addition. It's just different that for the subspace property, this is more about the closure property rather than a property about a mapping. Second property here for the linear transformation, it was we could either scale in the domain space or scale by C in the codomain space. This is a similar kind of concept, except we're just looking into closure. There's no transformation on the background of this one. So if you're thinking in those terms, it's pretty good carryover. Some of our examples will be subspaces, some of them will not be, and we're looking for a counterexample. So much like as we looked at counterexamples on these notes, same kind of concepts are going to come back. Let me see if I can find a counterexample. This was an idea of a counterexample. We took a vector u, a scalar c. We did t at c times u, got -2, 1. We took at c at t times u and got something different. So it violated that property right here. Same idea. If something is not a subspace, we're showing either it doesn't contain the zero vector, or you can find a counterexample, a specific vector u and v, such that the closure property fails. Much like we did on one of our very first, I think, example 2 on these notes. Or maybe this closure property fails for scalar multiplication. So it's nice to have a tie-in because it's a pretty abstract definition with several moving parts that we have to track through. Example 5 is just our first look into this one. I think we have enough time to get through this one in full. When we come back on Tuesday's class, we'll just be looking into more and more examples of subspaces and things that look like subspaces, but they actually aren't. Well, any questions at all, folks, before we check out that set H here? Okay, let's kind of spill the beans on this one. This one turns out to be a real subspace, and it seems like a silly one, right? It's a set that contains exactly one vector, the zero vector of R2. First, it asks, let H be 0, 0, so just the zero vector. Is H a subspace of R2? Well, the first thing you have to think about is, it had better be a subset of R2 right out of the gate. Well, it is a subset. 0, 0 has 2 entries, and every vector inside of R2 has 2 entries. So we can start off by saying H is a subset because, let me fill out the sentence better, is a subset of R2 because the element, only one, of H has 2 entries. So that's the first thing we have to check. It's possible we're looking into things where it's not even a subset at all. So that's a dead giveaway, and it ends the whole problem. If it's not a subset, we would just say it's not a subspace. And then you don't even have to look into parts A, B, and C. But passes the subset relationship. So we move on to the next thing. Let's go into part A. The largest vector space is R2, and we know what the zero vector there looks like. So we start by saying let 0 equals 0, 0 be the zero vector of R2. And, well, that's a really fast one to write down. We have to show that zero vector is in H. Well, it's automatic. H contains just one vector, 0, 0, so it's automatically in H. Again, it's kind of a silly problem in a way, right? Example 5 is more about just looking at how the proof works for each one of these, how to track through the definition before the problems get a little bit more messy. This is all about the concept itself. So not a lot to say, we can just say immediately. Then that zero vector we defined is in H because H contains one thing, that same vector. That's a fast check. Other times we might have to do something algebraically, look into properties. Maybe there's more going on with the set membership condition we have to check and so on. But that's the gist of it, or the gist of part A. Watch the color coding because where you grab your zero vector is important, and where you're trying to show it's included inside is important as well. Next, part B is fast as well. You pick two vectors from the set H itself. So we're just looking into H right here. We would start by saying, let U comma V be in H. You have to show closure holds on this one. Let's show that that absolutely must hold. Then U plus V is equal to, well, we just use the set theory membership condition. For U and V to be in H, there's not a lot of movement around here. Both U and V are 0, 0. So let's write them in. It's 0, 0 plus 0, 0, which is equal to 0, 0. And you know what? 0, 0 happens to be in H. That's the only element. Is in H. So we check that part. If we grab two vectors, well, there's really just one, but we did the best we could. Add them together, we got a vector in H. It satisfies this condition trivially because really there's just one vector. Like we said, this is a vector space, and by the way, it does have a name. This is called the trivial subspace of R2. And every vector space has a trivial subspace. It's the subspace that contains just the zero vector. And by this theorem, it's a bona fide vector space in its own right. It's just the world's most boring one. Nothing happens here. All the operations start on the same vector and end on the same vector. But we're looking into it again just for the sake of tracking the definition is the most important part. Next thing we'll do for part C, grab a vector in H, let U be in H, then, actually, let's grab a little bit more. We have to recall, we also need an arbitrary scalar, and let C be an R. Then we're checking this condition here, C times U. C times U is going to be C times 0, 0, because U can only be 0, 0. That kind of looks like a 6, though. Let me fix that one. Doesn't matter what the scalar C was. If you scale the zero vector with any scalar, you get the zero vector back. And this is in H. That means our work is done. We have something that's non-empty. It contains a zero vector. It's a subset of R2 automatically because R2 has two entries. Properties A, B, and C hold automatically as well. So all we have to say now to finish this off is, therefore, H is a subspace of R2. And that's tracking through this whole definition. Any questions at all, folks, running through this definition here? Okay, some of these go kind of fast. Some of them take a while because, again, there's a lot of details to show. No, I think the actual one does go a little bit faster. We've got about 5 minutes to spare, so let's take a look into this next one. Because we're learning this definition and it's a big one, I've just copy and pasted it all the way down. And here's the next example let's think about. H is a really nice set. It's a pretty cool set. But being a cool set, a convenient set, doesn't automatically mean it's a vector space, tragically. A is a set of n by n matrices, and that means they could be invertible. Set membership condition insists on invertibility. That's the invertible matrix theorem. We've collected it into one set H, the set of all square matrices of size n by n with a non-zero determinant. So H is the set of all invertible matrices. It turns out this is not a vector space. Something goes wrong here. It's not a vector space of R n by n, not because the subset relationship failed. Subset's just fine. These are square matrices, so they belong to Rn plus Rn by n. Something else goes wrong. Anyone see what the problem would be, thinking about this one? Yeah, good call on that one. Everything looks great about this, except actually it all falls apart the moment you go through the definitions. You take the zero vector of V. Let me highlight that better. V in this problem is Rn plus n, so we'll start by saying let Z, it's an n by n matrix, so it look like this. For it to be the zero vector, that just means all the entries in this n by n matrix are zero. That's one way to write out. If you just wrote Z equals Zij, where Zij equals 0, that would qualify as well. You'd want to say where I goes from 1 to n, j goes through 1 to n. It's kind of a long statement in the end, or just write out like this. I feel like I have to finish this out just to make it totally correct, where Ij equals 1, 2, all the way through n, because you have to say every entry is 0 in that way. But if you do that and look into the set membership condition, this is how you get inside the set H. Z is the zero vector of Rn by n. However, determinant of Z, well, it'd be the product of the main diagonal. It's just 0. Or just do a cofactor expansion down, say, column 1. It'd be zeros times a bunch of submatrices, all 0. You automatically get a determinant 0 when you work in the 0 matrix. And this tells us the following. We want to show the 0 vectors in H, but it fails. This shows Z is not in H. And so H is not a subspace of R n by n. And I mean, that's okay. Like we mentioned before, it feels like it should be a vector space or a subspace because it looks like a cool definition. But no, actually being a vector space or a subspace is a pretty restrictive set of conditions. You can't just put anything down here and make it work out. Determinant is not the right condition to get a subspace of Rn by n. There are a lot of cool subspaces of Rn by n, and we'll look into some of them. But any last questions at all, folks? Looks like a good stopping point for us today. Okay, we'll practice this definition more in the polynomial spaces so it doesn't feel like we looked into them for no reason. We'll look into examples of polynomial spaces that are subspaces or not subspaces. And then we'll also look into other things like, say, for example, this interesting subspace of C negative 1, 1, the space of all continuous functions from negative 1 to 1. All this work is pretty abstract, but subspaces are important, so we'll take the time to work these out carefully. But here is where the course starts to feel pretty similar as well. The absolute most important theorem in chapter 1, or excuse me, in chapter 4 is theorem 1. If you span a set of vectors, it is automatically a subspace of the vector space V, no matter what you're spanning. We're going to take massive advantage of that later on. This is where the course becomes a lot more concrete. Feels like what we've been doing all along. Well, have a great weekend, folks. If you have any other questions, I'll be happy to help. And we're getting through it. I realize this is abstract stuff, but read through this chapter 4.1 over, say, a couple times. It starts to connect and come together pretty well, I'd say. But have a great weekend, folks. We'll be back here on Tuesday. Thank you.
Thank you.